Alrighty, this is 5.5b, which is the second half of the lesson on solving trigonometric equations. For this lesson, you're definitely going to want to have that trig sheet out. Yesterday's lesson, we used substitution and we used factoring to help solve these problems. And today we're going to add one more step, and that's going to be using a trigonometric identity to help us. So how do you know when you're going to have to use a trigonometric identity? Well, when you look at this right here, you have sine squared and cosine in the same problem. Now, cosine x cannot be rewritten other than 1 over secant of x, so you're not going to be able to change that one. And you're not going to be able to factor it unless these are both the same term. So if we had 2y squared minus x, we wouldn't be able to t-chart it. We need to have the same variable, and in this case we need to have the same trig identity. So what I'm going to do is use one of my Pythagorean identities to change sine squared x, and again I'm changing sine squared x because I can't change cosine x. So 2 times 1 minus, so that's the only difference in this problem than what we did yesterday. So I'm just going to work through the problem real quick, and I'll chime in here and there, but it's pretty straightforward. You got to distribute. And then once you have it there, you're going to combine like terms. So 2 and negative 1. And then what am I going to do after this? I'm going to multiply both sides by negative 1. This is my personal preference because I don't like my leading coefficient to be negative. And it's just easier, but it's up to you. You can definitely t-chart with that negative there. I just tend to make less mistakes if it's not there, so I like to multiply both sides by negative 1. Then I'm going to t-chart. And I need it to have, I think I just did that backwards. Oh, nope, this is what I did backwards. Do you see that mistake I made? Right up here, negative 2 cosine squared x minus cosine x. So this should still be a minus, but then when I multiply it by the negative 1, it should be a plus. So there's that correction. Maybe you caught it. And then I'm going to split set, see what I get. So I'm going to split up the two factors. I'm going to set them equal to 0 so that I can use the zero product property, and then I'm going to see what my answer is. So cosine x is equal to 1/2. I'm going to figure out where does that happen. It's where my base of my triangle is positive 1/2, so it's those two numbers right there. That reference angle's got to be 60 degrees because opposite that angle is √3 over 2. So the first one is going to be pi over 3 plus 2n pi, or 2 pi n if you prefer. That's what we've been writing. Doesn't matter which way, either way is fine. And then you can come around here. I'm just going to check up at the initial problem just to see what it wants me to answer. So it doesn't tell me it has to be restricted. So this is going to be infinite solution, so I don't have to make a table or figure out anything else. These are good answers. I just have to finish up this side. Cosine of x is equal to negative 1 at pi. So there's my 3 answers for that one. So as you can see, it was very similar to the last few problems on yesterday's lesson. The only difference was that I had to use the trig identity in the first step, which is the same thing that I'm going to do here. So I have cosine 2x plus sine x equals 0. I am restricted to 0 over 2 pi, so when I do my answers, I need to be careful of that. Cosine 2x, we can change. Sine x we can't, so go to cosine 2x, and remember this is the double angle formula that has 3 different ways because it involves the Pythagorean. So you have to decide, do I want this one, or this one? And in this case, because sine is right here, and we want to keep it all consistent, so all in terms of sine, I'm going to take cosine 2x, and I'm going to write it as 1 minus 2 sine squared x. And then I have plus sine x equals 0. And then from there, what I'm going to do is put it in order. And you can see again we have a negative leading coefficient, so I'm going to multiply everything on each side by -1. And then we factor. If it's feeling repetitive to you, that's good. That means you're picking it up. If it's not, that's okay. Just a couple more practice problems will be helpful for you. And then I split set, see what I get. I'm going to do this one first because it's super easy. So there's only one answer. It would be pi over 2. Okay, I just did that one because I knew it was going to be easy. This one right here. So this is going to be the sine of x equals -1/2 when I subtract that 1 over and divide by 2. That means the heights of my triangle are -1/2, which means that's a 30-degree reference angle, or pi over 6. So the one that gets me there is 7 pi over 6. And the one that gets me here is going to be 11 pi over 6. So because I'm adding 2 pi each time once I go n to the first power, so we start with n is 0, and when n is 0, my answers are going to be pi over 2, 7 pi over 6, and 11 pi over 6. And when I switch over to 1, I'll be adding 2 pi, so if I'm adding 2 pi to something, I'm going to be bigger than 2 pi, so I won't be in that condition, so those are the 3 answers for that one. Moving right along to example 3. This one is a little tricky because you go sine x, cosine x, and you're like, hey, Wolken, you just said you can't change sine x, cosine x, so what are we going to do here? Nothing squared, we can't use the Pythagorean, what are we going to do? Well, you're going to use your trig identity sheet to find something that's close to what you see there. So the pattern that I see here is sine x, cosine x. So I'm looking and I'm like, well, sum of difference formulas have sine u, cosine u, these two do, so maybe, but then they also have this plus stuff here, and we don't have that, and I don't know a way to generate it, so that's not going to be right. And I'm scrolling down, just looking for that pattern, and then here I see sine u, cosine u, but I see a 2 in front. Well, guess what? You can multiply both sides of an equation by 2 fairly easily. And if you actually look at what this is equal to, it's equal to -1/2. So if I multiply both sides by 2, I generate 2 sine x cosine x equals -1. And I can rewrite this as the sine of 2x equals -1. And so now here we are at the point that we did yesterday, where anytime we had anything in with the x, we use substitution. So we're trying to find the sine of what angle equals -1. Well, the sine of 3 pi over 2 equals -1. But we didn't start with just alpha. Our angle was 2x, so we're going to re-substitute that back in. And then I'm going to multiply both sides by 1/2. It's the same thing as dividing by 2, but I think it's going to be a lot easier to work with our fractions over here if we leave it as multiplication by 1/2. That's going to be 3 pi over 4, and that's going to be pi n. So there's our infinite solution equation, but up here it does give us the condition that we want to be from 0 to 2 pi. We only have one x, which is nice. So when I plug in 0 for n, I get 3 pi over 4. When I plug in 1, I'm going to have to get common denominator, so that's going to give me 7 pi over 4, which is 1 and 3/4, so that's still in the 2 pi range. And then when I plug in 2, I'm going to be adding bigger than 2 pi, so 2 pi, which makes it bigger than 2 pi. So our only two answers are 3 pi over 4 and 7 pi over 4. And now on to example 4, which is our trickiest problem. So example 4, we're going to approach the same way we did example 3, and then we're going to hit a speed bump and then a barrier, and we'll see what we can do. So I'm going to put tricky on this one just so that you guys come back and study it. So this says cosine x minus sine x, and you're saying, hey, I only see cosine and sine again. I can't really change those, so what do I do? So then we look for a pattern. So you're looking through it and you're looking for cosine x minus sine x. You're just scrolling through these identities. Cosine x minus sine x. You have it squared right here, but hey, wait, maybe we can use this somehow, maybe not. Let's see what we can do. So what we're going to do is we are going to square both sides. But we're going to be careful when we square both sides because we cannot distribute that 2. We have to FOIL it out. So just a friendly reminder that that square around the parentheses means that you have repeated multiplication twice. And when this happens, when you square both sides, what happens is you create extraneous solutions. So anytime you square, you're always check for extraneous solutions. And that's done at the end once you have your answers. So now I'm going to FOIL this out, and I get cosine squared x minus 2 sine x cosine x plus sine squared x equals 1. And if you look right here and right here, I have cosine squared and sine squared, and they're the same sign, so they're going to combine to make 1. And I know some of you are seeing this right here, and we'll talk about that in just a second. So now what I'm going to do is get one side equal to 0. If I can, and in this case I can, because when I subtract 1 I get there. And this is where we can differ in our approach, and I'll show you both ways. So one person can go, okay, well this is equal to 0. This isn't equal to 1 like this problem up here. So since it's not equal to 1 and it's equal to 0, I can divide out this -2, and I can use the zero product property again. So sine x equals 0, cosine x. And this is again only because it so happens that the right side equals 0. So what happens is the sine of x is equal to 0 because it goes with y here and here. So I have 0 plus 2 pi n, and I have pi plus 2 pi n. And then we come over here and we do cosine, and it's going to equal 0 wherever x is 0, which happens at pi over 2 plus 2 pi n, and 3 pi over 2 plus 2 pi n. So what would our solutions be over the interval from 0 to 2 pi? Since that's a condition, they would be 0, pi over 2, pi, and 3 pi over 2. I'm not going to box this just yet because remember we have to check for extraneous solutions. So I'm going to just put a little check here. So we're going to start with x equals 0. Whenever you check, you need to plug it back into the original equation before you squared it. So it's the thing that was printed on the paper. So does cosine of 0 minus the sine of 0 equal -1? Well, cosine of 0, so here's 0, Cosine is 1, so I get 1 minus 0. Does that equal negative 1? Nope, it equals positive 1, so that's not a good solution. Then we'll move on to pi over 2. Cosine of pi over 2 minus the sine of pi over 2. Does that equal negative 1? Here's the cosine of, here's pi over 2 right here. The cosine is 0. Minus the sine is 1. Does that equal negative 1? Yes, negative 1 equals negative 1. Then we're going to do pi, plugging it in. Some of you can do this mentally. Some of us need to write it down so we don't make silly mistakes. Cosine of pi is over here. That's going to be negative 1 minus the sine of pi, which is 0. Guess what? That one works too. Let's see about that last one. So the cosine of 3 of pi over 2 is 0. So this little piece is 0, and then I'm subtracting the sine of 3 pi over 2, which is negative 1. So when I subtract that negative 1, it becomes positive 1, so that doesn't work. So my only two solutions for this problem are pi over 2 and pi. Before I show you something with your calculator, I just want to show you the other way to approach this problem. Because we did get negative 2 sine x cosine x, we could have used the double angle formula for sine. So let me show you what that looks like. I have it on the back of my paper so you can look at it and see if this is what your brain would have told you to do. So here we are at that step after we've squared and simplified. So the first thing I did was multiply both sides by negative 1. On the front side of this paper, we use the zero product property, but we could have chosen to take the left side and rewrite it as the sine of 2x. And then we're going to let alpha equal 2x, so we're like the sine of what angle equals 0. And that's going to happen at 0 and pi, so there's our two, alpha 1, alpha 2. But we didn't start with alpha, we started with 2x, so we got to work backwards. And so our answers are here. Well, then once I have here, I need my solutions over 0 to 2 pi, so I plug in here. And these are those same 4 solutions that we got, and then we would need to check those, and we would find that our only two answers that work are pi over 2 and pi. So that was just to show you that you can get to the exact same answer using a different method, just like so many of our identities. All right, so I'm going to take just a quick 2 minutes here to show you something in your calculator that we've done before. So for this problem right here, over the interval from 0 to 2 pi, we ended up with 3 solutions. So what I want to show you guys in your calculator, first you want to make sure you're in radian mode. Second, we're going to graph. So I'm going to go here, and if you notice, I already have this equation plugged in. It says 2 sine squared x. Well, your calculator can't, I haven't figured out how to get it to do sine squared x, so I do sine x times sine x, which is still sine squared x, minus cosine x, and then you'll see it also says minus 1. So just like we learned a couple of chapters ago, I'm plugging in the left side in my equation into y1 and the right side into y2, and then I'm going to hit graph, and this is what it looks like. Now I've also changed my window. So my window, I set the maximum, so the furthest right, I did 2 pi, and you couldn't see that, how I did that. So let me just, you hit the number 2, and then over here on the caret in blue is pi, so you hit second pi, and then enter, and then I'm going to scale, so each little tally mark on the graph is going to be scaled by pi divided by 2. And then I don't really care about the y's. So this is what my graph would look like. How many times do the red graph and the blue graph intersect? 1, 2, 3. If you have time to check your answers, you could always go second calc, pick option number 5 for intersect. And then remember, we just have to get really close to the point of intersection. So it says first curve. I'm going to come over to the first point of intersection and hit enter. Now I'm on Y2. This will tell me that up here. So I am going to hit enter again, and then it'll say guess. And my intersection is at 1.0471976. And you're like, yeah, Wilkin, but you don't let us answer in decimal form. Right. But use logic. You know things are in terms of pi. Pi divided by what would be approximately 1.04. Well, pi is 3.14, so if you take a look in your calculator and do pi divided by 3, there we go. That's what we just got, and that was one of our answers that we got. And you could go through and do that with each of your answers as well. One more time, let's take a look at this one right here. I'm going to do this one in my calculator. So I'm going to put in sine x and cosine x. Oh, don't do that. Sine x, close, cosine x, close. And then on this side I actually have negative 1/2, so make sure you hit negative instead of minus, and then graph. So what's graphing right now is sine x times cosine x, which if we wanted to graph that by hand, we would just have to make a table and go sine x times sine of 0 times the cosine of 0, and so on and so forth. And there is 1/2, and then you're looking and you're like, how many places does this intersect? And if you need to zoom, it's just at the bottom of those two curves right there, which is great because look, we have two answers as well. So then second calc, intersect, get really close to that first point of intersection, really close with the other line, and then guess. And it says 2.356192, which are like, I have no idea what that is, but when I did it by hand, I got 3 pi divided by 4, and look at that. That's the same answer in decimal approximation. Alrighty, that's it for today.